We will continue with our next guest, who is Philippe Morel from Bartlett in England. Philippe Morel is an architect, theorist, and entrepreneur, co-founder of EZCT Architecture and Design Research, and initiator and founding CEO of the large-scale 3D printing corporation X3 in 2015. He currently teaches as an associate professor at the Bartlett School of Architecture, University College London, where he is the director of the Architectural Computation program and the École Nationale Supérieure d'Architecture Paris-Malaquais, where he headed the Digital Knowledge Department, co-founded with Professor Girard. Before teaching at the Bartlett and in Paris-Malaquais, he was a seminar and studio professor at the Berlage Institute in Rotterdam and a history and theory seminar and AADRL tutor at the Architectural Association in London. In 2017, he co-edited the book Computational Politics and Architecture, From Digital Philosophy to the End of Work. In February 2007, he curated the exhibition Architecture Beyond Forms, the computational turn at the Maison de l'Architecture at the La Ville PACA in Marseille. Explicitly departing from Eisenman's PhD dissertation from 1963, The Formal Basis of Modern Architecture, the exhibition addressed both historically and theoretically the current linguistic and computational turns in architectural design. Philippe Morel has published more than 30 essays, lectured in many universities around the world: Harvard, GST, ETH Zurich, Columbia, Princeton, Pratt Institute, MIT, TU Delft, Lyon, Vienna, IAC, Centre Pompidou, etc. And he presented his work in numerous exhibitions: Centre Pompidou, Morel Museum, Tokyo, Museum of Art and Design in New York. His work and one of his offices are part of private and public collections, including Frax Center and Centre Pompidou permanent collections. I know Philippe for around 10 years, and the first conference that I organized on 3D printing in ETH Zurich decided to invite him, and it was an absolute amazing conference, and he participated in our talks in a ways that I was so proud of. I find him to be an incredible theorist and practitioner, and I'm incredibly proud to welcome him on stage here.
Thanks a lot. Thanks a lot, Carla, Nicola, Lesu, and also Adil on the ETH side for organizing this and inviting me. I'm really happy to be here with you today. So I will talk about, let's say, a few issues associated with intelligence and also with the concept of universality. So let's start. First of all, I love this because I think it could have been generated by Midjourney, a bit of a style transfer between Louis Kahn and Renzo Piano and Richard Rogers for the Centre Pompidou. So I think ultimately when we look at current architecture and postmodern architecture, by the way, let's say all these kind of style transfer issues, it's already here. I mean, all around, everywhere. But this is another story. I'm not going to talk too much about this today. I want to start with this sentence statement by Yann LeCun, you know, because we know that many people say, oh, deep learning is not as impressive as you think because it's mere interpolation resulting from glorified curve fitting. And LeCun, by the way, among many others, is saying that it's a wrong way to look at deep learning, I mean, it's not as easy as that, even if obviously it might be curve fitting. But we will see that it's not that simple. Okay. We experienced in the past few years an amazing evolution, I mean, amazing changes. Just like 2 years ago, we were still playing around with this kind of cheesy stuff. I mean, personally, I didn't want to play around too much with this because I was not so interested in that. But anyway, but nowadays we have to say that online it's a complete explosion of images and projects generated by artificial intelligence with Midjourney. And here are just a few images taken from different websites online by different designers, well known or a bit less known. But we have to admit that this change is absolutely mesmerizing. I mean, it's really amazing to think of that. We can see this kind of project as well, this kind of urban proposal, this kind of techniques which allows people to move from a sketch to a project. Sometimes we can also generate images in the style of a model to give a completely different feeling of what we have. And obviously we can also generate some kind of already quite complex geometries and architectural project. Obviously, if we would have to build this, it would be another story. But let's say that this is amazing, this is impressive, and we have to acknowledge this fact. Keep in mind that not so long ago, in the 80s, we were here. So it was not just a problem of the bad quality of the render. I mean, all of those things were to be modeled first. So it required really painstaking 3D modelization, then no less painstaking render work. And the results were rather bad, you know, we have to say. So if we look at the complexity we can generate today with no, I mean, with no 3D modeling, again, I insist, there's something here that needs to be discussed, and I believe that this thing probably has to deal with the idea of universality, but this is what we will address. So, again, AI, artificial landscape by Olivier Campagne, etc. So, yeah, this is massive. The change is massive. Obviously, when we look at the way at architecture as a building problem, there are some other way of looking at this issue of artificial intelligence, obviously associated with the issue of big data. And there's, I mean, it's a completely different branch. It's not something that we're already discussing during this conference. But let's keep in mind that it's not just about images and creative design. It's also about hardcore data, money, efficiency, etc. But again, either it is in art, in construction, in creative design, or in chemistry, including in quantum chemistry here, machine learning is absolutely everywhere, you know, just like everywhere. Because of that, some people say that we are entering a different, a completely new era in which the robots, I mean, a robot is really a dumb machine. I mean, the whole intelligence of the robot is in the software, obviously. I mean, it's pure software and pure, and nowadays more or less pure AI. And people like Geoffrey Hinton say that deep learning is going to be able to do everything. So I really want to insist on this word, everything. What does it mean? I mean, why can we do everything? Or why are we supposed to be able to do everything with machine learning? So I wanted to spend a bit of time looking at this, and at some point it's very much in line with my let's say almost philosophy of technique or technology, the way I'm looking at this, in line with Whitehead, who said that civilization advances by the number of important operations which we can perform without thinking of them, without thinking about them. And it's exactly what happens today with AI. I mean, it's everywhere. It allows us to do many things. We don't have to think about it, but precisely we have to think about it. I mean, that's the whole question. So the problem is a problem of generality, or at least or maybe a problem of universality. So this problem of universality and generality, I try to address it in my work as an educator. For example, here in Paris in 2017, we were already making use of artificial intelligence. I mean, the large language models didn't exist at that time. Also, the student didn't have access to, I mean, let's say big databases. So the idea was to try to collect images with text on web page by scrolling the web and trying to extract the similarities, I mean the correspondence between what we can detect as a shape in the image and what is present in the text, you know, written by architectural critics or whatever. Then by using NLP techniques, the students were able to rebuild some correspondence between a word and a spatial feature, let's say, and use that in a creative way to create, for example, here a plan. Here it's written grand séjour, salle de bain, WC séparé, means a big living room, a bathroom, and a toilet that should be separated, standalone. And as you can see, all these plans are not based on spatial things, but they are based on the description of what we would do today with prompt engineering, by the way. So this was done in 2017 in a master project in Paris with my students. And we can see here a bit of the work that has been done. In London, I will go very quickly through that. In London, in the Research Cluster 11, from 2017 until last year, I worked with Paul Poinet, and then I also worked with Julian Bessems here. So with Paul Poinet, we generated also, I mean, the students worked on project making use of machine learning, trying to connect machine learning with different kinds of, let's say, important issues today, like the lack of housing, the flexibility of the housing problem, how we can generate application so that the inhabitants will choose in real time the kind of living they want to, I mean, the kind of apartment they want to live in, etc., etc. And recently with Julian, we worked on La Défense in Paris. And here again, the students made, let's say, quite a massive use of machine learning in their project in many different ways. I mean, there was not like one way of making use of machine learning. It was very open, very experimental, but it led, in most cases, to highly convincing results. So it started with analyzing the landscape, extracting features, trying to see if we can, I mean, training the model. Maybe sometime it was connected with more classical method like this one, just based on the use of cellular automata. So many, let's say, many hybridations did happen in this work. So I just show you a couple of images so that I let's say I frame my discourse, and also you will know a bit more about me and what I'm doing, either in academia or, as I said, in my personal work. So here are a couple of images. Trying to rebuild, to reconstruct 3D geometries based on the use of 2D maps. Okay, and more recently, because I changed my position at the Bartlett. Now I'm leading the architectural computation program. So the approach in the AC program is slightly different. It's a bit less oriented towards design. It's more oriented toward, let's say, I would say something which is at the intersection of engineering and architectural design. It's more of a problem-solving approach that students have to deal with. So the title of the work of the student are self-explaining. If you read this title, reinforcement learning deep Q agents, learning difference within Poincaré hyperbolic. Okay, that one is a bit too long. Let's go for this one on the bottom right. Automated architectural modeling, a design toolkit for architectural 3D models using generative AI algorithm. Or on the bottom left, exploring the visualization of sound, machine learning classification of urban sound and its visual dynamic representation. So you see in the title of this thesis that the approach is slightly different. It's less design-based and a bit more oriented towards generic problem solving. So you can get more information about that on the Bartlett website. There's quite a lot of things. My personal work, I have to say, I always looked for generalization in my practice. When I was a student in 2000, I was not satisfied by this. I really wanted to understand what was behind each of these icons. Obviously, it's impossible, but I tried as much as possible. And this is when I started to use Mathematica, because I just wanted to start from a blank page like this. It was, let's say, a necessity for me to understand what's behind the curtain, let's say, but also I was not happy with this because I didn't find what real design was about. Starting from a blank page, for me, that's really the essence of design, the essence of creation. Creation almost implies that there's nothing when you start with. Obviously, it never happens because you have a lot of things in your brain and there's a whole weight of history. So it's an illusion, this kind of blank page, but still I was happy with that illusion and I kept being happy with it. Another thing is that I was also interested in manipulating not geometrical primitives, like here, but symbols. For me, it was essential to manipulate symbols because, that's the essence of writing, but that's also the essence of modern mathematics. Mathematics is about symbolic representation, especially when we speak about algebra and not geometry. And finally, I wanted to have access to a tool which allows us to do everything we want. And I was happy with Mathematica because, if people are knowledgeable in quantum mechanics, they can do quantum mechanics, obviously, with that very tool. But we can also teach design. This is a class I gave in 2019. It was about teaching Mathematica to the student. Letting them play with a graphic, almost like graphic design and painterly related things. So it was a base. It was just used to, again, to teach programming to the student, but also computation and some basic concept in programming and computation, like recursion or iteration, or this kind of really basic things. So my work is about this. Then I applied Mathematica in 2003 for creating this kind of patterns, which was a set design at the Centre Pompidou non-standard architecture exhibition. So all of that was done with with Mathematica. You see here the ribbon, this kind of things where all the iconography was printed, and the different steps I went through. This was my master thesis in architecture. This master thesis was about trying to understand a bit of differential geometry, some interesting concept having to deal with geometry like developable surfaces, curvature, mean curvature, normal curvature, max, min, Gaussian curvature, etc. So then I applied this to the analysis of different kinds of surfaces. I came up with an approach of surfaces which was based on the use of iso curvature patterns. The iso curvature patterns are were quite well known, especially the minimal and maximal curvature patterns. But one that was not really used was the iso-Gaussian curvature pattern. So I introduced this iso-Gaussian curvature pattern as a model of self-adaptive discretization pattern that would make the fabrication of non-developable surfaces easier. Then I worked on the use of genetic algorithms for the generation of this chair project. It was a proof of concept that we can use discrete topological optimization for the generation of structures. I show you here a quick video. Yeah, it plays. So generating chairs, and then also using exactly the same approach to generate a small pavilion for the Serossi pavilion competition in Paris. You will see this just after in the second part. This project was considered by some people, including like Mario Campo or Patrick Schumacher, as a kind of birth of the discrete style in architecture. I have to say I was not that interested in the issue of style, and I'm not interested in the issue of style today. But yeah, I mean, it happens. So this was used for the generation of the pavilion, of the Serossi pavilion in Paris. It was about using genetic algorithm to optimize the quantity of light that goes into a tiny building, so that the light, even if we have extremely complex geometries, so that the light could be equally distributed throughout the building. Which is one of the most important parameters when we want to exhibit paintings or sculpture or any kind of artwork. I kept working on this issue of discrete geometries. Slightly later, I wanted to scale things up, so I said, okay, but this is kind of interesting, this voxel, it's definitely universal. The problem is that how can we scale this? I mean, would it be possible to create an entire building? So I was also, in a very visual and almost metaphorical way, very much influenced by this drawing by Konrad Zuse, one of the computer science pioneer in Germany in 1931. And I started to be interested in what's called, I mean, it's not just discrete geometry, it's integer geometry. I mean, using a geometry which is not based on real numbers, but also not based on anything else than pure integers, not even rational or whatever. So that, in fact, it would be completely binary. I mean, either it's 1 or 2 or 3, but there's nothing in between. And I was interested in what would be the, let's say, the formal and geometric output of this if we constrain ourselves in using this pure integer-based geometry. So I created a small construction component, which is a universal component. So I called it U cube, universal cube. So that could be assembled in all direction, and it's a kind of three-dimensional Lego block that would be stiff in any kind of direction you might envision. Here is a drawing of this component, and the result is this project, the Universal House project. So this Universal House is made of this universal cube, this U cube, three-dimensional component. But obviously, obviously, based on that, the construction system would follow. So we would have cladding panels that would be also perfectly modular, etc., etc. Oops, sorry. I don't know what happens here. Oh, apologize. I don't know what I did. I jumped to the end. So, too bad. So the problem is that when we use this, obviously everything is a bit fragile. So how can we do, how can we make this completely stiff? I decided that probably the solution would be to have tiny holes in this and to pour in some fiber reinforced concrete in the entire structures. So I started to develop this kind of three-dimensional fiber reinforced grid in different ways. The cool thing is that we can even imagine to have different shapes, different geometries, so that locally speaking, we can make them bigger or smaller to adapt to the quantity of material that we would need in this project. And then, based on that, we started to, with my office, to investigate something a bit more ambitious. So we used a three-dimensional sand mold to cast more complex fiber reinforced structure. Obviously, when I say that I'm interested in the concept of universality, I believe it's really evident here. I was interested in trying to, let's say, to see if we could imagine a kind of modern version or a contemporary version of that work, you know, by Bell, for example, or by Shukov, or Buckminster Fuller, or also Raj Rewal here in India, an absolutely amazing building. So we worked on this three-dimensional structure that are made of, again, of concrete and not made of steel, but fiber reinforced concrete. And slightly we moved because this U-cube idea was good, but at some point it's so difficult to make it in let's say at a one-to-one scale that I said, okay, it's too complex. I mean, somebody else will do it. I quit with this. Let's use a more easy method. So we use three-dimensional sand molds like this. We made a couple of prototypes. This was fabricated. These sand molds were printed in Germany by Voxeljet in 2012, 2011. And then in 2012, we ended up with this prototype, which is a three-dimensional fiber reinforced, ultra high performance fiber reinforced concrete lattice. In black, you see the sand molds. And in gray, you see the cement. We applied this to different projects, like a staircase, unfortunately never built, and also some other project making use of genetic algorithms and Mathematica. But luckily, we had some other occasion to apply this approach. But here again, we changed the way we did it. We 3D printed molds made of clay that could be 100% recyclable because the clay is not cooked, it's raw clay. So we pour in the concrete, then with water we just remove the clay, and we just remove the water, we take the clay again, and we start again. So let's say this explains my two paths, you know, of my two lines of interest. On one way, the universality of discrete geometry and computation, and on the other way, the universality of 3D printing, because I also believe, by the way, that 3D printing is a universal construction method. I might be wrong, but yeah, basically, I believe that's it. So this led me to the design of this structure in 2012 with my office. At that time, we were convinced that we would build this, making use of what's on the left, making use of sand molds. But as everything in France is so slow, in the meantime, between the design and the realization of the project, in the meantime, I had the opportunity to create a 3D printing company. So finally, when we had to build the project, we had a new technique at our disposal, and this new technique was about 3D printing let's say the concrete mold, making use of high-performance concrete, and casting it also high-performance concrete, but with different kinds of fibers. And this is what we did. But as you can see, conceptually speaking, it's really the same approach. I mean, we just replace the sand mold by high-performance concrete. So we ended up in this. And then with this 3D printing company, we built a couple of other things, a small pavilion in France, like nodes at the scale of, big nodes for construction, for potentially large building. And recently, the last work I've done personally is this. Making use of statistical method to organize images as graph in an exhibition organized by Frédéric Miguero at the Centre Pompidou about artificial intelligence, by the way, about neurons. So for that, I used Mathematica. For each image, so the image were part of an iconography that was created and selected by the curator of the exhibition. So I search online all the kind of text that I could find about each of these image, mainly using Wikipedia as a kind of ultimate reference. So I aspired Wikipedia. Then you see, for example, here it's the kind of word you have for one painting. Or one drawing or whatever. And then I created different parameters and different criteria to create my own, let's say, connectivity model. I didn't use deep learning, or I didn't use machine learning. It was pure statistical analysis. So looking at similarities between words, how much time, that word or this word appear in the corpus, and then trying to find correspondence between all of that. So it was quite a lot of work, creating weighted graphs, similarity matrices, etc., etc. But ultimately, it ended up in this kind of things printed at very large scale in the exhibition. So it was a way to read, let's say, visually speaking. It was a bit of a classical work, but I enjoyed it. And now on the side of curating and writing, Nicolas mentioned that. In 2007 in Marseille, in the south of France, I organized this exhibition, Architecture Beyond Forms, the computational turn, which was dedicated to the evolution of architecture starting from Peter Eisenman in 1963, his PhD thesis, the formal basis of modern architecture, and trying to address the linguistic turn in architecture. For the very first time, I presented this now very famous wall by Fabio and Matthias. In Paris, I also organized a few events dedicated to artificial intelligence, to the digital philosophy, to the end of work, and different things like this in 2015 and 2010, 2015, 2016, etc. So, people will be, the audience will be able to look at my work here. So, as you can see, in what I've done, I was really looking for, let's say, the first principles and looking for explanation in architecture. And I ended up with this very deep interest in the concept of universality in architecture, or universalities in architecture. So I will present two kinds of universalities: the past universalities in architecture, which is about a mechanistic worldview, which is mostly about geometry. So clearly here there's two parallel paths in the history of architecture. I believe that the one taken by machine learning today is fundamentally different from this one. So this path is highly mechanistic, philosophically speaking. It starts from Descartes, from La Métrie with the homme machine, with the perspective of Paolo Uccello or Piero della Francesca, but also Alberti, by the way. Let's say we can follow this line of thought, which is mechanistic but also highly geometrical in the history of the last 400 years in architecture. We can see this in the work of Gaspard Monge. And as you can see, Gaspard Monge was also looking for some universality. So first, he spoke about creating a well-written treatise on a purely descriptive but rigorous geometry. So this idea of rigor was obviously present. It's part of the scientific revolution in any case. But he was also interested, as he says, so to speak, in creating a common language that would be necessary for the workshop manager to direct the work, but also for the workers who must carry it out. And he believes that by the generality of its processes, the descriptive geometry offers even the most sagacious young people the means to exercise their faculties and develop their intelligence. So it's true that we cannot underestimate the role of descriptive geometry in the history of architecture, as it became a kind of de facto standard for architectural representation until very recently, let's say. Until the disappearing of this kind of handwork. It was influential on Durand, and because this descriptive geometry was also, let's say, working hand in hand with a mechanistic worldview, this mechanistic worldview was also present in the work of Le Corbusier. Le Corbusier himself, who was mostly interested in geometry and very, very little in the revolutions, in the mathematical revolution happening during his time, which was an algebraic mathematical revolution. So the main concept was the one of form. Obviously, again, form understood as a geometrical problem, but also as a mechanical problem. And this lasted quite for a long time, because if you look at this project on the right by Diller and Scofidio in 1990, it's still a completely mechanistic worldview that you have here. So this mechanistic worldview is typically the one of the Industrial Revolution. At some point, it's also the one of Miss and Philip Johnson, and it was also the one that was, let's say, put on a kind of pedestal at the Museum of Modern Art in 1932 during the International Style exhibition. It was also the one of the late modernist style by architect, like Paul Rudolph here. But the problem is that it didn't work. I mean, something went wrong. This kind of universality went wrong. What went wrong? This is what we will try to answer. In any case, the form, the modernist form, didn't work. And you know what? Mies van der Rohe himself understood that something was not properly working, because when he was interrogated by Arthur Drexler, Mies himself, Drexler asked Mies, how do you spend your day? This was in an interview in the 60s before the death of Mies. And Mies said, we get up in the morning, we sit on the edge of the bed, and we think, what the hell went wrong? We showed them what to do. Why don't they do it? So, I mean, for Mies believes that he showed the path towards good architecture, good universal architecture, but the problem is that people didn't follow that path was that Mies considered really good. But maybe Mies himself did some mistake, because when you look at the Illinois Institute of Technology, the project is obviously on a purely architectural viewpoint absolutely beautiful. But when you look at the reality of technology, I mean, maybe visually speaking, it looks a bit similar, but conceptually speaking, there's a huge gap. I mean, there's nothing in common between this image on the left and this image on the right, because the image on the right exists because of digital technologies. I mean, it exists because we have logistics, because we can trace the goods and the parcels, because we have FedEx, UPS, and other companies like this. So again, in fact, conceptually speaking, there was something in the modernist discourse which was lacking, because the modernist discourse was interested in the structure as something fixed, as something which is outside, and it didn't pay enough attention to what happened inside. In the history of architecture, ironically speaking, this happens a long time ago at Versailles. Because the classical architects were interested in Versailles from the outside. But I mean, what was interesting in Versailles, what was happening inside, all the court and all the micro societies that was happening in Versailles. So in fact, when we look at the history of thinking in the 60s, definitely, if we want to learn something about architecture, we should definitely take some distance with a simplistic version of Mies and look at those people who understood technology in a much deeper way. I mean, Guy Debord, obviously, but also Jacques Ellul, who understood technology as a system, which was also not something that was really well understood by modernist architects. And also, we need to look at the postmodern architecture and postmodern conditions theorized by Lyotard and also by Jameson. But again, here, I warn people about another mistake which has been done, according to me at least, which has been done by Jameson, is that Jameson did not pay enough attention to the issue of technology, because he speaks about the cultural logic of late capitalism, while in fact we should be much more speaking about the technological logic of late capitalism, or maybe the computational logic, what I call myself the computational logic of late capitalism. So basically the main error, the main mistake is that the modernist concept of universality didn't pay enough attention to the evolution of history. I mean, it's not necessarily antagonic. You know, we can have universality while paying attention to evolution, you know. But in the modernist discourse, universality is like suspended in time. You know, it's something which does not evolve. While obviously, as a Marxist theorist, Gramsci said, in history, in social life, nothing stays rigid or final, and nothing will ever be. And I think this is well illustrated by this image, you know, the Ford Chapel in the US. I mean, when Ford created the Ford Model T, I'm sure it didn't really imagine that one day his car would serve as a mobile chapel. And this is exactly what history is about. You know, it's about emergence, it's about new practices, new ways of appropriation of technology. And in 1954, one guy, Asger Jorn, who was also part of the founding team of the International Situationist, was really, let's say, prescient about that. He wrote in 1954 that rationalist functionalists, because of their conception of standardization, believed that we could reach the ideal and definitive forms of objects relevant to man. Today's evolution shows that this static conception is wrong. The only way to avoid the anarchy of change is to understand the laws of its transformation and to use them, basically. So people try to go in that direction. When we look at the history of architecture after the 50s, when we look at Bruno Zevi, for example, who tried to introduce some sort of organicism in architecture, or when we look at the parametric architecture exhibition at the Milan Triennale in 1960, or when we look which is, by the way, the very first use of the word parametric in architecture. Or when we look at this drawing by Andrea Bronzi, whose title is Structure in Liquefaction in 1968, we see that architects wanted to capture this idea of evolution. Some, like Bernard Rudowski, were looking at a different logic. They said that this concept of evolution can be understood if we look at the vernacular architecture, because it embeds a kind of self-adaptation logic in the world. But still, when we look at that, what we see is that most architectural theorists believed that the problem in architecture is a problem of language, you know, and it happened also in art. At the end of the 60s and at the very beginning of the 70s, language became the important topic, the hot topic in art. And at some point, it was meaningful, you know, it was right to do this. So people started, like Jameson, to write about language as a prison house. For example, artists said that we should analyze language because it's not transparent, it embeds like biases. By the way, it's exactly also something that people say today, you know. If you look at wokeism discourses or things like that, I mean, many people also say that it's a matter of language, which personally I don't believe. I don't believe it's a matter of language, but this is another issue. So the architect, the proto-postmodern architect like John Haydock, started to distort the modernist language of architecture. So here we can clearly identify the fact that John Haydock stretched the Mies van der Rohe countryside house. We can also see John Haydock here rereading the famous painting by Mondrian, starting again to distort the regular grid-based language of modernist architecture. And some other people making use of shape grammars or space syntax. For example, this is a pure space syntax work at the end of the 70s or early 80s by Bill Illier, for example. They also tried to analyze the architecture and again, either as a question of space or as a question of language, but in most cases as a problem of language. So it's really at the very end of the 70s that we see the postmodern architecture being theorized, even if according to me it started much before. But in any case, the main concept, which will be still operational in the 80s, is the one of language. So the postmodern architecture, the deconstructivist architecture, is about changing the architectural language. Only one guy, Robert Venturi, at some point understood the postmodern architecture in a slightly different way, saying that it's not about space, but it's also not completely about language, it's about communication, which is something I totally agree with. So language, algorithmic aesthetics were, let's say, fashionable in the 70s and at the beginning of the 80s. Ultimately, the revolution came from the guy who started to pay attention to the dynamic, to the real dynamic of forms. For example, this kind of swarm phenomena, and coming up with algorithm to analyze what really happens. And philosophically speaking, I still believe that the philosopher who was the most acute was Paul Virilio, theorizing the fact that in the modernist world, there is the possibility of the accident, or let's say the accident is an intrinsic feature of modernism, while modernist architects believed at the contrary, that modernism was about a kind of endless continuation of an original intellectual project. So what are the present universalities in architecture? Conceptually speaking, I would say it's about a statistical and quantum mechanistic worldview. And practically speaking, it's about computation, which is a mechanization of abstraction. And this mechanization of abstraction, it evolved according to a completely different intellectual path. Right, we could say it started with Descartes, but very quickly it started to diverge and to follow its own line when we look at the history of science. According to me, it went through Lagrange as a kind of amazingly interesting reference. Lagrange was really proud in the mechanic analytic to say that in this work, no figure will be found in this work. The method I present, so quote, require neither construction nor geometrical or mechanical argument, but solely algebraic operations subject to a regular and uniform procedure. So, I mean, Lagrange uses the word procedure, the word algebraic operation, and he even, let's say, denies let's say, the domination of geometry and mechanical arguments. And this is also what will happen with Leibniz, with the Characteristica Universalis, or the ratiocinae. Okay, forget it, I won't be able to pronounce it. This is also Calculus Ratiocinator, sorry. And this is also what will happen with the École de Port-Royal in logical thought in France. who understood also that the issue of grammar was important, but as we will see, grammar in the Port-Royal school is associated with logic, and so it's a completely different line of thought compared to what I was mentioning before. This line of thought goes through Babbage, through Boole, Georges Boole, with this absolutely amazing, I mean, for me, it's one of the most amazing statement and page in the history of science and in the global history of thinking, for example, when we can read that for Georges Boole, if X is hard, Y is elastic, and Z is metals, then we can express non-elastic metals as Z multiplied by 1 minus Y. I mean, this is really the birth of what we are doing today. I mean, it's where everything started. I mean, the formalization of the language as a pure mathematical problem. I mean, most people know, of course, in a very, let's say, because it's part of the popular culture, I mean, the Boolean logic, 0 and 1, you know, but I mean, what really matters is this, I mean, being able to compute on sentences, because these sentences have been transformed first into an algebraic problem. So at the same time, De Morgan was also proposing his calculus of inference, so the formal logic and the calculus of inference. And also at the same time, philosophically speaking, Auguste Comte, with the philosophy positive, proposed a hierarchy of science in which everything is based on mathematics. So let's say mathematics is really the basis of all the upcoming knowledge. This line of thought, Comte positivism, will be also developed by another kind of positivism, which will be called neo-positivism or logical positivism, by Russell and Whitehead in the Principia Mathematica. And this will be connected to something which will be also very influential and which will be non-geometrical, non-mechanistic. I mean, it's mechanistic in a philosophical way, but it's not mechanistic in a formal way, let's say. It's algebraic in a formal way. And this is the birth of thermodynamic. So basically, this line of thought, recently, in the history of architecture, some people like Mario Carpo believe that it should be associated with the issue of writing. I believe we should be a bit, let's say, cautious, careful with this, because as I'm explaining here, I mean, the technology is obviously associated with this very wide concept of writing or text or discourse. But at the same time, if we only pay attention to this, there's something extremely important that we are missing. If we look at the printing press, and if we analyze the printing press, conceptually speaking, there's an element which is missing, which is lacking, and this element is in fact the feedback. Because when you print letters, basically those letters have no effect whatsoever on the printing press itself. I mean, it's static. Again, it's a very modernist way of looking at things. You know, the printed letters and text are not part of a machine control language. So what was missing, in fact, was the concept of feedback. I mean, we needed the concept of feedback so that when you print something, what is printed can be put back as an input in the machine. And obviously, this never existed in any printing press in the history of printing. And it also didn't exist in the history of the Jacquard loom, for example, before the invention of the computer. So I'm not denying the fact that this Jacquard loom is super important in the history of technology. What I'm saying is that, again, here, there's something which is missing, conceptually speaking. And what's missing is the fact that those punch cards are not, I mean, once they are printed, they have no effect on the program which creates new punch cards, basically. And this lack of feedback loop, it was still present in the late calculating machine in the early 60s in Italy. So again, when we look at this, we see that we have the feeling that things are, let's say, it's a problem of language, but in a static way. So here there's two things that we should notice. First, we needed the concept of feedback, we needed Wiener, etc. But we also have to pay attention that ultimately, maybe it's not even language. Maybe it's not even language, because when we look at the large language model, there's no language into the large language model. So it's a bit weird to have to have that name for something which is absolutely not about language at all. It could be about carrots. I mean, I don't know anything, but it's not about language. It's much closer to what Shannon was theorizing in the mathematical theory of communication. It's pure statistics. I mean, it's a matter of similarities, of algebraic distance and similarities between things. So I insist on that. One important conceptual evolution happened with Wiener. I know cybernetics is not really fashionable anymore, but it's not a problem. What's important is that without having the possibility of a feedback loop, we wouldn't have computers, basically. Because, I mean, a computer is a machine which can reprogram itself. And if it cannot reprogram itself, it's just a printing machine. It's not a computer. So basically, we had different concepts of universalities. We had the one of Turing. We had the universality of algebra, which was proven right in the mid-19th century, which means that everything which is geometrical can be transformed into algebra, algorithm, and program. And obviously, for us as architects, this universality directly led to the possibility of this kind of machines with which we can produce more or less anything. So here we have two dinosaurs. On the left, we have the last dinosaurs of the mechanical age, and on the right, we have the first dinosaurs of the computational age. And in fact, the main importance is obviously conceptual. I mean, conceptually, there are two completely different machines. The one on the right is universal. The one on the left is not. It's as simple as that. And this universality led very quickly in the popular culture to the concept of simulation, which was also treated by Jean Baudrillard. I mean, we can simulate everything. So conceptually speaking, this new situation, I call it computationalism. And this universality of computation is based on a few things. So the universality of the logic gate, again here, it's almost a kind of miracle of reductionism. The fact that we can do everything with just an AND or an OR gate, which again is so amazingly beautiful when we think of it. The universality of the Turing machine, the universality of the neural network that we have here. This universality of the neural network, at the very beginning, it was missing. If you know a bit the history of artificial intelligence or the history of neural networks, you might know that at the very beginning with the perceptron by Rosenblatt, one of the really harsh critics came from Minsky. And Minsky proved that with the perceptron of Rosenblatt, which has only one input layer and no intermediate, no hidden layer, you cannot compute everything. It's not a Turing machine. It's not a Turing machine. But then, and by the way, it opens the gate to the winter, to the artificial intelligence winter, because people believe, okay, we cannot compute everything we want with this, so let's forget about it. But then, people on an empirical basis, they discovered that with one hidden layer, with more neurons, I mean, either more neurons or more layers, so we can extend the neural network in width or in depth. In depth is deep learning, and in width it's mostly the number of parameters. I mean, even if we add layers, we also add parameters, obviously. But so then, much later, at the end of the 80s, people came up with this concept of universal approximation, with this theorem of universal approximation. And finally, we knew that the neural network were universal Turing machine, which became something extremely important. So, in fact, we had classical approximation method, polynomial fitting. I mean, all this is part of history, obviously. We had a universal approximation theorem by Weierstrass, who proved that with a polynomial, we can approximate any function. We just need to have an infinitely long polynomials with degrees, with increasing degrees, or the Stone-Weierstrass theorem, it's the same. And we also have approximation method in machine learning. Some of them are universal approximator, some of them are not. So this approximation, this universal approximation theorem, it came from different authors, different mathematicians, Sibenko and Ornik, more or less at the same time in 1989 and 91. So it's not that old when we think of it, but it completely changed the game. It completely changed the game because then people could, let's say, project themselves in deep learning, let's say, in neural network, because they knew for sure, thanks to a theorem, that deep learning could be able to do everything. Exactly what Hinton said. You know, Hinton said deep learning can do everything, but mostly it can say so because it has been proven that we can compute anything. So going back to Yann LeCun, Yann LeCun say, okay, people say that deep learning is just an interpolation problem resulting from glorified Q fitting. So basically, Q fitting is what we have in the history of math, and that was obviously super important for engineering and architecture and everything around. But as Yann LeCun say, the problem is that we cannot say this because in high dimension, there's no such thing as interpolation. In high dimension, everything is extrapolation, according to Yann LeCun. And it creates, this opens, I mean, this is because of the regularities, by the way, of the regularities of the data. But it creates something really interesting on a philosophical level, because then some people say, but if it is not about Q fitting, then what is it? You know, I mean, what is deep learning if it's not about Q fitting? And I mean, it's a very, it looks like an easy question, but it's a very deep question. So Q fitting is this, for the one of you who don't really know what we are speaking about. It's just like you have some data and you try to find a line which interpolate the data. And if the interpolation is good, then we can imagine that very close by the extrapolation will be good as well. You know, it does not always work, but it's the thing. So we have this as a universality, and then we need something else. Let's say we need a new hypothesis, and this new hypothesis it's the hypothesis of artificial general intelligence. Even if we don't believe in the possibility of this, it doesn't matter. What's interesting is that as an hypothesis, ultimately, it's what deep learning is based on at the very moment. And even if people don't say it, ultimately that's what they have in mind. So then it becomes a problem of intelligence, the universality of intelligence, the universality of the machine intelligence, and the universality of human intelligence. So human intelligence is defined, broadly speaking, as a mental quality which consists of the ability to learn from experience, to adapt to new situations, to understand and manipulate abstract concepts, to use knowledge to manipulate one's environment. When we look a bit more closely, we see that the definition of human intelligence is not that simple, that easy. There's a whole history about that in cognitive science. Some people, for example, define different factors. So Spearman defines the G factor, which is a general intelligence factor, while he also defines the S factor, which is a specific cognition. So we could say if artificial intelligence is not cure-fitting, then maybe it's intelligence in a human sense, but because some people say it's not general yet, so maybe we can say, okay, then it's a specific cognition. So artificial intelligence as we know it today is about the S factor of Spearman. So there are some different correlation, and we can link what happens in artificial intelligence to this search for the nature of intelligence, to the principle of cognition, and to this universality of the human intelligence. I will go quickly on that, but clearly, if you read Spearman, you see that he's looking for the nature of intelligence, and is looking at for scientific principles of cognition. So I go quickly on that. Then we have different approach to thinking. Obviously, connectionism is the one which might be the most operational at the very moment in artificial intelligence, and we have also many different definitions of artificial intelligence, and also many different definitions of deep learning. But I mean, what's interesting with this definition is that whatever the one you choose, it's always linked to human intelligence. Intelligence is about getting better over time. It's what Spearman said 80 years ago. Intelligence is a computational part of the ability to achieve goals in the world. Achieving goals is also associated with human intelligence. So what we can say is that so far there's no concept of intelligence which is truly computational. All the concepts of intelligence we use in artificial intelligence are man-related. They are defined according to humans, and they are not defined according to the machine. They are not intrinsic to the machine. Anyway, what's the conclusion from this? We say, okay, AI is, some people believe that AI is just glorified cure-fitting, so interpolation problem, very much in line with the history of mathematics. Some people say it's not that, but then what is it? So one of the possible answers is, okay, it's a problem of intelligence. We refer to human intelligence to define artificial intelligence. So we could say that the partial machine intelligence is should be approached according to this factor S from Spearman. The artificial general intelligence could be approached according to the factor G from Spearman. Then two open questions. Is artificial general intelligence possible? obviously it's machine intelligence by definition. And the second question, does architecture necessitate artificial general intelligence? My feeling, because it's mostly a feeling, is that brains are not more powerful than current computers. I mean, if we look back at history, I mean, keep in mind, some people believe that language was a kind of ultimate frontier, that a computer would never be able to do good translation. I mean, the translation which is done by my computer are better than the one I'm doing myself and better than the ones that professional translators are also doing in many cases. And most of all, in large language models, it's not about language. So the belief that language was the ultimate frontier is maybe completely wrong, because large language models are not about language, you know. And even if it was about language, it does it well. You know, it does the job. So I believe that brains are not more powerful than current computers. And the answer to question 2 about architecture, a CPU contains all possible architectures that could ever be invented by the next trillion generations of people, I mean, especially architects. So I believe that in any case, as of today, we don't need artificial general intelligence for doing any kind of architecture we can imagine. But there is a parameter which is important, and it's the changing parameters, is the input. You know, the inputs are changing constantly because those inputs are nothing less than history. And the history is the moving parameter in let's say in the problem. So yeah, I want to end up with this. Thank you.
I can start off. Wow. It is a tremendous body of work. Thank you for sharing. You just took us from all your career, and I was fascinated. I couldn't, yeah. So my question is about language, because I'm so glad that you talk about Wolfram Mathematica, because I was listening to one of his lectures, and he was saying that from history we know that since the Greeks, they are trying to encode the way that we think, and then they thought that they will do it through logic. And then we have Boole with the Boolean logic as well, trying to do the same. And now we have this, what you said is not about language, but these large language models. So I'm curious to know what you think about other ways of encoding our thinking that is not only about talking, but many other ways of thinking. Like, we also think in images, we also think in feelings, we also think in other ways. And I think these may be these inputs that you're saying that are influencing what these universal machines are doing, that are not only that do not have to do only with language as well.
I believe that images are language.
As well.
I think ultimately they are language. They are a kind of more compressed version, or it's not even about compression. I believe that images are just a different coding, you know, a different encoding of things. So my feeling is that whatever we do as humans, either we look at images, we work with images, or we work with text, or etc. Ultimately, we do exactly what the computer does, is that we reduce everything to purely numerical and then algebraic and logical operation in the brain. So I would say that maybe after all this evolution in artificial intelligence, it brings us back to the original hypothesis about intelligence coming from von Neumann, for example, in the computer and the brain, in this beautiful piece of writing by von Neumann, where everything is about discrete computation. Even if obviously there's some analogous things that also happen in the brain. I mean, these analogous things that happen in the brain are more like they are a mean. They are not. It's just a tool, let's say. But the fundamental things that happens in the brain, I really believe that ultimately it's pure discrete signal exchange and pure statistics. I don't know. For a very long time in history, we believed that, for example, what happened in the body was happening because of God or because of some sort of force, obscure force that we didn't know what it was. And then, thanks to the evolution of science, we saw that it was just like stupid chemical reactions. I mean, what happens during that digestion, for example, it's chemistry, nothing else. It's basic chemistry. So my hypothesis is why the brain should be smarter than the liver. I think what happens in the brain is just raw computation, nothing else. And it doesn't really matter if it's about images, text, or any other kind of encoding.
I have a question, it's not really a question.
And again, I want to insist for the very first time, maybe this is why we should not underestimate the importance of large language model. Conceptually speaking, as a turning point in the history of Western science. For the very first time, we have something which is amazingly efficient regarding language-based question, while there's no concept of language in the process. I mean, it's pure statistic, it's pure computation of distance between words, etc. I mean, large language models know nothing about language. And this is why, let's say, all these things, ChatGPT, etc. It's definitely a very deep revolution on a daily basis, and for the history of capitalist society, because it has consequences on productivity, on the way we produce things, etc. So for that, it's important. But it's also important on a completely different level, and that level is conceptual, and it has to be understood within the framework of the history of Western science, according to me. And again, it's about the fact that for the very first time, we understand that maybe language problems are not linguistic.
Thank you, Philippe. I really enjoyed your lecture, and it's incredible. It's also quite unfortunate because a lot of your work that you showed in the kind of also the computation of structural forms which are then to be 3D printed is actually, you are one of the people who initiated this thing, and somehow I do not see this being created back to you. Like the 3D printing that I see today is, I mean, in the US is pretty horrible.
Yeah.
and there's no abstraction that they're trying to just build a classic house with. So I cannot even imagine that this is not referenced. But yeah, this sometimes, yeah, I don't know. Things, what goes around comes around.
Yeah, exactly. So. It's
But then I do have some comments. It's very because it was a very fast talk and complicated, and I did not take notes. So I do have some challenges there. The first one would be a feedback that you said, okay, feedback is what from a machine to any machine, that the feedback is the missing factor. Somehow, something similar to feedback, yes, but I'm not sure if it's feedback, because feedback comes from Wiener and cybernetics, which kind of is post-computation, and also a lot to do with the closed systems of thermodynamics. But if we look at how computation came to be with the Turing and Church, and especially with Church, since you're interested in lambda calculus, it was somehow this guide by Hilbert of trying to find this Entscheidungsproblem, to try to find an algorithm which could be prove the not correctness but consistency of
Yes.
itself. Yeah.
Yes.
And then, you know, Turing did a Turing machine which is able to do exactly what you call feedback by means of states, and the church which is able to do this by means of nesting functions. So symbolizing functions, like literally taking functions to be symbolic entities,
Yeah,
and then
a recursive function
Yeah.
is based on feedback. Otherwise, it's not recursive. Yeah.
yeah,
I mean, you need to bring the output as an input.
exactly.
Yes.
So yes, it is kind of feedback, but somehow if we say feedback in the sense of cybernetics, then I don't know. It kind of gets a weird connotation for me.
Yeah, I would say that the concept of feedback was in the air in any case, and it was manipulated, and it was used by mathematicians. You know, all mathematicians who were defining recursive functions, we could say that they invented this idea of feedback before Wiener, for example. I insisted on Wiener because probably he was the one who insisted on the fact that this concept of feedback was universal. It was not just key for recursive functions, for example. It was everywhere in the world. It was part of our biological life. I mean, without the concept of feedback, there's no life, because it's about self-regulation and all of that. So I would say definitely the important revolution, or let's say what's the importance of what Wiener brought with cybernetics is not so much the feedback alone, because this was used. Also, by the way, Wiener knows that. I mean, he says that it was used by James Watt, you know, in the steam engine and etc. What Wiener brought is a new vision of feedback as a completely universal concept that encompasses everything in the world, from math to biology to physics.
Yeah.
So
Psychology also. He wanted
Or-
to treat people,
yes,
people's psychological problems with feedback machines.
yes. So
I don't know, but let's come to the large language models. So you
Yeah.
mentioned, which I agree, but you said universality of approximation. So universal approximation theorem, and obviously Minsky was wrong there and did a lot of undoing had to be done. And universal approximation theorem somehow does create a code which is able to not compute everything, but to approximate everything. That's why it's called universal approximation theorem, not a universal computation theorem, which is something which is already done by Turing. So what I think is going on there, what my problem with it is, and why I would still think that coding itself is prior to language and prior to everything, is that approximation is what these models do, and then we have an input which allows us to, it's a kind of from X getting some Y. And it's done through approximation, and some call it curve fitting. Yes, I think it's too simple. But within these large language models, then we see that these prompts become actually so important that if you want to get any good result from these models, the prompt becomes an art form, which just tells me that the prompt itself is another type of code. But what is the computer? So then the computer is the large language model. And my question, is that computer Turing complete? And I claim it's not.
No, I mean, obviously computers are Turing complete, and regarding the neural network, it has also been proven that on top of the universal approximation theorem, it has been proven that there are also Turing complete systems. So I would say everything is ready for a very deep revolution in computing, in which we won't use neural network as software executed on classical Turing machine, but we will use neural network as a Turing, as a machine, you know. So we will have neural network executed on neural processing system, which, by the way, already exists. You know, Google developed its own neural processing unit called the NPU. So it's not the CPU, it's the NPU. Because the computation are done by neural networks. So I would say, yeah, to answer the first part of your question, yes, the neural network are Turing equivalent. It's again, it's a mathematical fact nowadays. There are also universal approximators. Obviously, we can, I mean, there's always some amazingly high-end mathematical problems with this kind of concept. It's clear, which goes far beyond my understanding. And to answer your second question, I would say prompt engineering. So I agree with you that the prompt is important, but the prompt in itself is conceptually not different from any other input, right? I mean, it's just an input like anything else around, you know? And it has also been shown, at least on an empirical level, experimentally speaking, but it might be the case that soon it will be, it will become a mathematical theorem as well. But it has already been shown experimentally that artificial intelligence systems are better at writing prompts than humans. So, you know, here again, we close the loop with this kind of recursive, primal recursivity of computation, in which, I mean, the concept of computation and the concept of neural network is so powerful. The universality of computation is such a powerful concept that nothing is left to humans, let's say, including the prompt. Because again, the machines are already better at writing good prompts. So it's very puzzling, you know. I would say it's. I mean, those experiments by computer scientists are extremely challenging, intellectually speaking. I think it's extremely challenging because we really have the feeling that whatever the way we approach the problem, we end up with the superiority of the machine, which, at least to me, is a very fascinating question. And this is why some high-end mathematicians end up with almost, extremely speculative hypothesis, and I would say almost metaphysical hypothesis, saying, like Penrose, saying that what happened in the brain is quantum-based, and it cannot be replicated by a classical machine. So that, in a sense, it gives us the feeling that he wants to save, he wants to save the human part. But maybe there's nothing to save. Again, maybe simply we have reached a point in which already in the history of Western science, while it's only the beginning of history, 400 years, humans are on Earth for 3 million years. So 400 years of Western science is absolutely nothing. And what's fascinating is that already we have reached a point where we produce machines that are so amazingly good, you know? So if we start extrapolating, if we make almost science fiction-based hypothesis, what's gonna be in 1,000 years? What kind of machine we will have? So this is why I believe all these questions, and again, if we look back at history, what we considered as evidence or ultimate truth, they might prove themselves to be wrong. And for me, the best example is that there's no way to make a distinction between let's say, the attention brought to dedicated to language by the history of Western philosophy, for example, but also science. I mean, the whole history of Western philosophy is about language. The funny thing is that even Foucault, who is not considered as a representative of a linguistic approach of philosophy, even Foucault says in his course at Collège de France, he said, we can't say that the whole history of Western philosophy is about language. If we remove the problem of language, we can clearly ask ourselves what's left, you know? And so even if we disagree with Foucault, even if we say, okay, maybe it's not 100% about language, we can at least say it's a lot about language. You find language problems in Plato, in Aristotle, in Leibniz, and obviously in 20th century philosophy with a linguistic turn, you know. So, and finally, we have these large language models, better than anything we could ever imagine, and the problem of language vanished because it's not involved at all in large language models.
Yep, I strongly disagree, but obviously some other people will have to ask other questions.
Yeah, thank you for this talk, Philippe. So many things to discuss and to pick up. I wanted to ask on that very notion of the idea of the large language model, and that there's no language in a large language model. Because on one hand, I found it striking how in the beginning you were saying, like, we find these things amazing because they have a mirroring quality to us. But then when you posit them as kind of universal, as a universal machine, I feel that there's a kind of contradiction, maybe. I'm not sure, because we had this yesterday, that discussion of what would happen if you would train the models, the transformer architectures that are used on language, on something completely different, on DNA sequences or on animal sounds or whatever. What would happen? And I think that this is very interesting because it surfaces the question that maybe the kind of intelligence that we seem to have found in the large language models seem intelligent to us because it's the primary mode of how we reason, how we communicate, and so on. But this does not mean that there's an intelligence outside of the language that these things are trained on. And then the question becomes a bit abstract and difficult, but then there might be a possibility. Either one says, okay, language is primary and language is intelligence because this is how we reason. But then one can also say intelligence renders itself through language, and so what we can get in a large language model, it's a fraction of that kind of intelligence that is very suited to us as human beings, but might not be universal in that sense too. And so in that sense, I think the universal Turing machine, or like this computation, maybe to some extent is more abstract, more universal still than the large language model and the neural nets.
Yeah, I see what you mean. I would say, regarding the question about intelligence and language, we will never be able to assess a truly alien intelligence, a truly alien form of intelligence by definition, because we cannot put ourselves outside of ourselves. I mean, we can only analyze things through our feelings, sense, sensations, and we have only one brain, So what we can identify as intelligence will always be, and it's a kind of logical problem, will always be defined according to our own intelligence. But yes, still the challenge might be, one of the real challenge of the future will be to come up with concepts of intelligence that are not anthropomorphic, I would say. First, this will be necessary. It's difficult, but at the same time, it's also not completely impossible. Think of what happens in the history of physics. You know, of course, the laws of quantum physics are defined by yourself. So just because of that, we could say they are anthropomorphic, because they are produced by humans. But when we look at the laws of quantum physics, we can hardly say they are anthropomorphic. You know, they are human. I mean, they are produced by humans, but they don't look like us. So I believe one of the challenges in artificial intelligence is this one. I mean, producing definitions of intelligence that are obviously produced by us, but that won't be associated in a way or another to concepts that are anthropomorphic. And at the moment, it didn't happen. I mean, all the definitions you will find on artificial intelligence are all anthropomorphic in a way or another. So this will be probably one of the great endeavors of the science of the 21st century, if it happens. And the second thing regarding intelligence and language, yes, we are humans, and the only way to express things is through language. So I kind of agree with you until a certain point that for us, we consider language as a sign of intelligence, and we also define intelligence according to the language. So it goes in both directions. But we could also imagine that spending a whole life with somebody who never speaks, but does things in an amazingly intelligent way, you know, like an artisan, you know, a craftsman, who would never speak. And by looking at the behavior of this person, we would definitely be able to say if that person is intelligent or not. And then the concept we would probably refer to would be the capabilities of abstraction. So, for example, if you build a piano, you know, you need to transform a few things in abstract components. Otherwise, it will take you 100 years to build a piano. It will be pure experimental craftsmanship, you know. So if you want to do it in a smart way, you will need abstraction. So I don't agree with the fact that intelligence is about language, and I don't agree. Yes, yeah, but I mean, no. What I want to say is that I believe this connection, this almost natural connection between language and intelligence, can be completely broken now, and maybe the large language models are showing us that what we considered as a deep relation, almost as an evidence in the history of Western philosophy and science, was maybe a wrong hypothesis. And I believe that it's more about abstraction. And by the way, abstraction is also probably the most important concept for the machines, for the computers. So the more we move, the more we go towards this importance of abstraction against the importance of encoding. But that's philosophical hypothesis. Okay, so thanks a lot.
Thank you so much.